Okay, we're kicking off. The plan, we've got a couple people jumping in. Hello, the plan is doing some more molecular nodes development, but this time I want to try and I want to see if I can build a full PDB parser just entirely inside nodes. So to begin with, we're going to build a very basic parser with strings. So for the longest time, currently inside molecular nodes, you could go select res_id custom, and you could put in a string here, and we would have to build a custom node group that would then give you a selection, and inside here it's a bunch of node groups we'd have to generate with Python on the fly. But I think if we go string, we want residue 5, 10, 20 to 40, and residues 50 to 75. We should be able to just handle this string inside of geometry nodes. So let's have a go at that. Split string. Separator. That should give us a list. Trim. I should clean up any white space. Then we repeat. Length. This we can get rid of. Boolean. Okay. And so the plan is we have a list. We have a list of items, and we just need to pass them individually. And we basically iterate over that. And for each loop, we say if this true, or if that true, or if that true, and the final result comes out. And so if we get list item, so each repeat we get a single list item, match, and if it contains dash, because we have either a dash or not, and if it contains a dash we do one thing, if it contains a dash we do another thing. So we say switch closure, evaluate closure, Boolean selection, plug that in, and the input will be a string. So we basically want a function that evaluates a string into a selection, and that compounds and iterates, and the result becomes our selection. So closure. So if it doesn't contain that, we do a simple string to value int equal oops. And so we say if the residue ID is equal to this value, true. And that's our parser if there isn't a thing, and if there is, we say split string dash get list item, first item, second item, string to value. And we say it's greater than or equal. And we'll say this is less than or equal. And we say that's res ID. We say and. And that's our function for evaluating a string. Let's test this out. So we say select res ID. Say select res ID string. Now we plug that in. And we get nothing, and we say residues 1 to 30. And we get absolutely nothing. What about 1 to 200? What? Res ID. Okay, it starts at 340. That's why. 1 to 500. Still nothing. Contains that, otherwise that. Less than or equal, greater than or equal, split, trim. Okay. Range 1, this is... Okay, we definitely should be getting something. What if we just do 440? Okay, so our single selections are working. It's our range is not. Split, trim, get our first and our last to value. Value is greater than that. Value is less than that. One to 500. Why is it we not working? We split by comma. We iterate that many times, we get the index. If it shall we use the same thing? Range separator. Why don't we just say just that one? Okay, we do get something. Was I just way off? Res ID. Greater than or equal. Less than or equal. 1000. Why is that showing greater than? Our value is oh, I just had that the wrong way around. Okay. 1 to 300. Nice. So we want residues 1 to 300, 500 to 600. Oh, that works great. Okay. We have a simple part, a simple selection. I could make that more complex, but I'll leave that for now and we'll get onto the what I was thinking of doing, which is text load import text. So if I go home, if I import a PDB, let's go and I say import text. One BNA. This, okay. We have our PDB file, which is, if we just say split string, import text. Special. There we go. If we say length, okay, so we have 80 characters, a perfect PDB file. And if we so if we So here's our PDB file. And so we want everything that starts with atom. So we say filter list starts with atom. We are cooking. And I have the spec here. So if we okay, so this gives us our usable lines, length, points, so we have a point cloud for 1 point for each atom. And we can say our atom ID is an integer slice string from 7 to 11. 7 is 4 long. That's our atom ID. And we say to string to value. That's trim. There we go. And that goes in there. Get list item, index, that works already. Ridiculous. Okay. So what we want is bundle type. We want molecular nodes PDB pass. And we say bundle items. And if we say geometry, and we call this combine bundle, length, we call this name, atom ID, join bundle. repeat evaluate closure. Get bundle item closure list item. Evaluate closure. Geometry closure. And we want that bundle over there. What about an all atom parser with DFT on each atom? Look, let's parse a single PDB file first with nodes, and then we'll talk about doing other things. I don't even know what you mean by DFT on each atom, but this can go here. Okay, so now in theory, cool, atom ID is there. And so this is our atom ID parsing. And now we can just have a whole bunch of things, and we solve all the wave functions. We solve every wave function. I don't know, that's a lot of set position. We can do it if we work together. You know what? I was wrong to doubt you. You're so right. We can do it. Let's do X, Y, Z, X, Y. Oh, no, not that one. Z. What are we? Atom name, so we want positions 31 and they're 7 long. So 31, 7, float, combine. Let's hide that. Make sure we're working on just this. Okay, that is working. Why? Oh, this is atom ID. This is position. Where we want to set bundle. Hey Quackaroony, we're passing some text files. We are going, hopefully, to pass this text file. It's not a CSV, it's a yeah, so We're really working out the closures and the bundles and all that junk. I just had some success doing a little parser here where we can input a string and get a selection out using some closures and some of the string nodes and our lists. And so I'm now trying to do that on a bigger scale, more nodes, more strings. Bundle item. This will be, I'm still a little confused about bundles, when they need to be inside each other and that sort of thing. Some ID. This is going to be position. We need to get list item, join string, / string closure, if I can spell in closure right. We are still getting nothing. Oh, we want bundle type and we want molecular nodes, wildcard. Item ID closure. Okay. Why are we getting nothing? Come on. So we have our strings and we're just trying to slice them up. So if we slice the string, we're getting our string. We trim our string, string to value. That's working. And we're getting our closure. Oh, fucking hell. We are not repeating enough times. Length. Oh my god, plug in. Yeah, that's still not working. List length, bundled list items, definitely getting our closures. Interface, input, output, geometry, geometry. So we're getting our closures, but they're just not being evaluated properly. Get bundle item. Like the Atom ID is working. Why is this one not working? Because I unplugged it. Now it's fucking working. Let's go. What the heck did I do here? Jesus. Let's This is our x coordinate. String 31. So 31, 39, 47. 31, 39, 47. Oh my god, that's working. We need to scale. 0.1. Ah, and there we go. Why is that complaining? Points to mesh. Ball and stick. And if we find some bonds, okay, we're sort of getting somewhere. Okay. Good job. Yeah, thank you. I am glad that okay, so spheres. Oops. Oh, I don't like the look of that. Why is it so perfectly on the grid? Oh, because that should be, yeah, I was not being accurate enough. There we go. Ah, beautiful. Okay. That's atom ID parsing. This is position parsing. I think I can just do this into the same thing. Position. Sees molecule neuron activation. Yeah, boy. This activates my neurons. Currently, let's turn off the compositor. Disabled. So currently we don't have any color information, so we're just passing atom ID, which is just an integer, position, which is just an integer. So we've got these ones. We want alternate location, element symbol, 77 to 78. So it starts at 77, length 2. Uh, 77, length 2, int. No, not int, because this is going to be a string. Oh, that's annoying. Okay, so we need a string. Is it crazy to use a bundle as a dictionary lookup? Quackerini, am I crazy? H1 helium 2. Can I remember my elements? I want to say lithium. Yikes. 3. Carbon. No, carbon's not 4, carbon's 6. What is Jesus Christ? Periodic table. This is embarrassing. Beryllium, boron. Oh, fake elements. Beryllium. Oh no, these are all also. We want these to be integer, 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 integer. Integer, boron, just B. 1, 2, 3, 4, 5. Carbon. Now we're getting to the interesting ones. What? Why did that? I mean, I don't know if you have a better way. The only alternative I can think of is integer input list. I mean, sorry, field to list index switch. I might do both of these and compare which one. And we do a string. We say node index let's go the first 16 elements because I think I don't need anything more than that. Helium, oh, sorry, hydrogen, helium, beryllium, boron, no, fuck, lithium, beryllium, boron, oh, God, these numbers are gonna mess with my head. Yeah, fuck this. Yeah, so unfortunately, in the storage file, like, so if we look at our strings filter, so this is the where it's encoding what element it is, and it's encoded with the letter rather than the number. So I need to turn that letter into a number because we have list fields now, but we don't have list attributes now, unfortunately. And so hydrogen, helium, beryllium, boron, no, fucking hell, lithium, beryllium, boron, carbon, nitrogen, oxygen. That's all I got. Fluorine, neon. Just F. Jesus, how did I ever pass chemistry? Fluorine, neon. Can't you load in a list? Razor45, hello! Hello, everyone. To get everyone up to speed, this is a PDB file. So this is what protein structures and molecular structures, the format that they come in. I mean, this is an old format. It's a newer one now, but this is the simpler of the formats. And I'm trying to pass this information, which is not a text file, a CSV, and pass it into geometry nodes, so building our own parser. And we have some success already. So we already have this entirely parsed with geometry nodes. And the way we are approaching it gets kind of messy, but is kind of elegant, I like to think. So we are basically, we have a bunch of columns. So if we read in our file, you can see we get the head of our text file. We split it by a line break, which gives us every line in the text file. So we're off to a great start. We only currently care about make a string that has everything. Yeah, I am thinking about that approach, Quackaroonie. But we have every line, and we really only care about these lines, currently at least, that start with atom. And so we can filter our list of strings with that, and we get all of our atoms lists, atom lines, and basically these, they're very regular and they're defined by a specification. And so we can say our positions, so our X, Y, and Z coordinates are characters 31 to 38, blah, blah, blah. And this defines our parser here. So we have a little closure and we say, slice our string from 31, 7 characters along, trim it, convert it to a float, and we do that for our X, Y, and Z. And we combine that X, Y, Z, scale it into our world coordinates, set the position, and basically we can keep adding parsers to our bundle, and then for every item in our bundle parser, we loop over, evaluate that parser, and store the attribute. And then we get our parser. And so we have, currently we're passing our atom ID and our position, which is very cool. We've got a whole bunch of other attributes to add, but we basically just like write a parser here, join it into the bundle, and it will then be applied. An absolutely cursed way to do string index is theoretically possible with find in string, and yeah. The other way I'm thinking about is if I have a list and I mask the list. I'll do that in a second. mrouth121. What about CIF files? CIF files, yes. PDB files are simpler currently, so I'm just starting with PDB files. I mean, I've already got all these parsers written in Python. PDB, like I already have these parsers written in Python, and I use them inside molecular nodes. But I want to just try and do it inside geometry nodes. So we got sodium, magnesium, so sodium, oh my god, sodium, magnesium, aluminium, silicon, sodium, magnesium, aluminium, silicon, phosphorus is what we're after, phosphorus and sulfur, and then we go P, and we go S. Cool. And so now we say index. We go into there. So now we have a list of strings, and so this is currently pulling out our elements. And to convert this, so we trim it, and we say equal this one. That's doing some weird things. I think we need to do closure to list. And we say length. And we say closure. And oh, this is going to be gross. We say get list item index compare filter get list item 0 atomic number. So this should now convert. Is that doing it right? Oxygen, carbon, carbon, oxygen. 8668. Hey, there we go. Yeah, so this is kind of cursed. So this is how we can convert a list of strings. So what we're doing is we are masking a list of strings, or we're comparing it, and then it'll have one correct item in there. And then we use that to mask a list, and that gives us a single list item, and we just select that list item. And that gives us our lookup. And we could also do this with combine bundle. If we did, I only care about a few for this one. So hydrogen is 1. We will also care about carbon, which is 6. Nitrogen, which is 7. Oxygen, which is 8. Phosphorus, which is 15. and sulfur, which is 16. So we could also do it that we get bundle item integer. And that also does the same thing. How, so closure to list. Scene time. So for that, we're looking at around 0.1 to 0.13. This is definitely slower. So our little bundle lookup is better. Not by much, but it is definitely better. Yeah, because that's staying under 0.2, and this occasionally goes up to 0.2, 0.3. Well, there you have it. We have our little lookup. Dictionary lookup to convert element atomic number. Okay, cool. So now we can store that. We can yes. So if we have a look down here and we do scene time. So if we do this field masking, which I mean, it makes sense because we're dealing with more stuff. But we're getting, I might change this to a larger structure for some molecular nodes. .pdb. Oh, I only have the one structure. Okay, we'll keep it at this. But we're getting about 0. High teens, sometimes 20, sometimes 30. And this, we're like pretty consistently low teens, almost 0.10. So using the bundle as a lookup. I assume it's just because like we create a bundle and we just use this dictionary lookup compared to creating two lists, masking those lists. Like maybe if we pre-computed these lists and cached them compared to, yeah. But yeah, it actually works as like a dictionary lookup, which is pretty cool. I hadn't thought about using bundles like that until now, but so we now store named attribute, integer atomic number, get list item, index, and we combine that up here, and this is our atomic number. And now it's all broken. What's going on? Oh my god, it works. We've bloody passed a PDB file and we have elements. Yeah, the dopamine did hit. Look at that shit. Let's do a more complex file. So this is AUCW. AUCW. So if we turn that one off, filter. Oof, that, oh my god, it works. Let's turn off our bond finding. Let's turn this into spheres. Oh my god. And our selections work. Okay, color attribute random. So what we haven't passed is our chain ID information, which is going to be more complex because we got some chains in here, but they're all. What is our parser at? So our parser is at what, 12, 15 milliseconds? Not ideal, but you know, not terrible. The colors, I want it all. Oh yeah, we want it all. Like, that's the good stuff. So we have pass atomic number. So now the easy the easy mode was looking up a list of known IDs, which is basically your elements, because we know that they're always going to have these values. But if we look at all of you can move down, and so now we want this, the ABC chain ID, and chain identifier character 22. So we want 22 length 1. Why does that give us blank? Characters 22, yeah, so we start at 21. Are all of these off by 1? I don't know. So we have our chain ID, which will be a what do we doing? Structure AUCW, AUCW. Okay, A1 is a chain. Yeah, cool. So A, A1, C, and D. So how do we, an unknown list of items. We need to convert to integers. How the heck do we do that? I did create a node for that. This is exactly where pull requests created by me. It's exactly where this node would come in handy because we need to find the unique values. So our unique strings. And there's really no way to do that other than to iterate every value, which is gross. So length, repeat, repeat. We get rid of that and we integer. So this is our count. Fifth Mizuka, oh, that's a long name. Hello, how we doing? If we use the same dictionary lookup, so we're creating a dictionary of integers. Get bundle item. Oh, this is this is going to be some terrible performance. Our bundle item is an integer, so we get list item. So we have our list of strings. We get our individual string. We attempt to get it from the bundle, which checks if it exists. If it exists, we just continue on. If not exists, we store our current count. Join bundle. Switch bundle. So if not exists, if exists, skip. If not exist, are you just trying to count the number of atoms in a chain? Sadly, I'm not. That would be a much simpler thing to try and do. So we have multiple chains, and each chain, we got A, we got A1, we got C, and we got D. And I can't store that value because currently we don't have string attributes. We have string fields, but we don't have string attributes. So I can't store this on the geometry. So I need to first convert it to an integer. And so the only way to do that, and to convert it to an integer, like currently a sort of approach is I basically say in alphabetical order, A, B, C, D, we have alphabetical order, and we just store those in, instead of this string, we store that integer, and then we can use that for lookup later on for colors and all sorts of stuff. What are you working on or trying to create? I'm trying to create a PDB file parser. So to import, well, I mean, I can already import protein structures using Python into Blender. This is an experiment trying to get entirely with geometry nodes. Can I replicate that functionality? It's going to be slow and it's going to be bad, but it's going to work. So we get our list item. And we attempt to get that. That checks whether or not it exists. If it exists, let's say if it exists, we continue, we just pass it on and we go on to the next thing. If it doesn't exist, we store the current count as the item and we increment that by 1. So if exists, pass along, otherwise add 1 to our count. That should give us a oh my god, that actually worked. With hashing, I could use hashing. I suppose if we hash, we still run into the same issue that, yeah, it needs to be stored on geometry. The alternative would be, the alternative could be, because we are working entirely in geometry nodes, if I store, oh my god, of course, we can store bundle combine bundle chain IDs string so this could be an option as well, which would kind of be, as long as we're storing the original list, then we can kind of use it as attribute lookup. As long as, like, if we use the index as a mask into the list to look up, then we always have access to the original strings without having to do all this bullshit. And then we can just store our so then if we Because now if I say get geometry bundle, get bundle item, string list, and if I just use this as our string array lookup, oh my god, string array lookup, if I can learn how to type, and we say get list item, we say that's the list, that's the item, oh actually, and we say this is index. So now we say chain ID, bundle path not found. Oh, what is there? Oh, chain IDs. Well, why did I call it that? Chain ID. And then we get that. And importantly, get list item. Why we should have equal, let's say C. Why isn't that evaluating as a field properly? Quackaroony, help me. Like, that's getting me my list. And then all I'm, did I properly set that as index? Yeah. Get list item. Why doesn't this? I suppose because it's not going to display it in the attribute sheet because we still don't have string attributes. Oh, of course. A. Oh, that still doesn't work. Oh wait, what did I do? Hey, there we go. Yeah, thank you. They did get deleted. So now we can select chains. So we can select our string attribute. We're basically using a string attribute without having access to string attributes by storing them as bundles and treating the index of that list basically as an attribute for the point domain. And we can then basically, so that basically gives us, with a bundle, well, sorry, with a list, we can now basically have access to any arbitrary attribute that a list can handle. So that works. And so, all right. I mean, we always then need a geometry input to be able to access that bundle, to be able to get that. But in theory, just like our select res ID string, we can do the same sort of thing. Okay, so actually, let's test this also with our we can do the same thing with our elements. Element. And test for carbon. Yeah, and we select our carbons. And we don't need to convert it. We don't need to convert it to an integer. Hoya! So I can just do away with all of that if I instead just keep the original. Okay, that's cool. Is that gonna work? It won't work with the existing stuff because, okay, so if we repeat select res ID string, so this one, string, and we can just say our string is so we can't have a Boolean output, like we can't have no input with a Boolean output because we need our bundle source. But if instead we have evaluate closure, if our selections were closures, which I suppose would make more sense. Then we can have our selections be closures, which can be evaluated with access to the geometry. We don't need to just work with fields. I know Jacques has talked about a field zone, which would basically do exactly this, where if we have geometry input and geometry, when we have selection output, so then we have that in here. And now we have trim, get list item, evaluate closure, okay, so what we would need this capture where we have geometry in, geometry out. We say atoms, and we say atoms. And this is where we say okay, so we say capture attribute evaluate closure, get list item, let's just call this string. Okay, and then this recursively evaluates and so this we call Yeah, I don't know about... I mean, it'll definitely work, but it'll definitely be messy. So that selects carbon and nitrogen. If we go... Oh my god, that works. God, closures are so messy. Like, look at this gaping gap here. I hate them. They're so visually messy, but very powerful. Okay, so that lets us okay, so we could do element string selections, but it would have to be a closure, and it would have to be evaluated on geometry. That's purely a limitation of not having string attributes. Okay. Let's instead, oh, that's so slow, 76 milliseconds. Just to pass a try and get unique values and turn it into a lookup. Oh, that's so horrible. The alternative closure is if we just do that same iteration and we store our bundle item and we just don't care. We get our list item. We don't check first. And we instead just hash that string. And we just store that each time. And that would basically just overwrite. Okay, that's much faster. And then we get an entirely random number. Bundle path. And field to list. Closure to list. If we do index, Length. Closure. So this is basically, can we overwrite? Oh no, what am I talking about? I already have that. Well, there's our unique values. A list of unique values. What if I to value like base 26 or something? It's still really slow. What if we combine bundle? Can we get multi-threaded? Join bundle. That's much slower. And we get our duplicate keys, but that's okay. But yeah, that's much slower. So the best way to get a unique list of items is currently to repeatedly store that and just override it. Scene time. So that's what, around 50, and if we string to value instead, almost basically exactly the same thing. So we hash the value. God, that's so expensive just to get unique values. $50 milliseconds just to get a list of 4 strings. But good to explore it. Yeah, holy performance cost Quackerini. This fucking sucks. But I can't think of a better way to try and do that if I was to go this route. What, how long is this? So, a list of strings with 4 unique values that are about 16,000 items takes 50 milliseconds to pass. What if we instead go to our 1 BNA? So if we have only 500 elements, it only takes 2 milliseconds, which is still not good. Okay, but regardless, let's turn this into a... Wait, okay, and that's compared to... So this is at least definitely faster than this, which is basically half as fast, half the speed. Because we're doing some checking, and this we're just overriding regardless of what it is. If we instead don't hash a value and we just store it, int. So if we just store a string, we're looking at mid to high 40s, very occasionally pushing 50. If we hash it, then we're consistently hitting around 50. So hashing is definitely slower, which makes sense. So if instead, to get a unique list of strings, we use a repeat zone and iterate every, actually, closure. No, there's nothing else I can think of there. And you can't. No, I cannot beat those allegations. I'm coming for Chimera. Welcome, Clockwork. We are having some success, actually. This structure you see right here is parsed entirely using geometry nodes. No Python involved. The performance is not good, but the point is that it can work. So for anyone who has joined, well, look, let me walk you through the nightmare of these nodes. So we can import a text file, which our PDB file, our CIF file, they're just text files. At this point, I think you should just get unique list items merged. Yeah, in the last geometry nodes module meeting, Hans did specifically say he wants that node merged, but we wanted to, because it was so last minute, we wanted to wait a little bit and see how people end up using lists to see how it should function ideally. And so we're already running up against exactly that of like, this is a use case, and it's like, okay, this is now a use case, and so we can design against that. So hopefully we have that notes and I can use it later. But to get anyone else up to speed, we have a string, or we have a file. We can pass that as a string, and we literally just get the entire text file, which you can see here. Accurate gene sequences into DNA nodes. Yes, you definitely can, and we can work on that. Yeah, we can pass like gen bank files and that sort of thing, definitely. So we get our text file, we split the string by a line break, and we literally get a list that is our PDB file inside of geometry nodes. So we have one list or one string per line inside that file. And so you can finally encode some messages in the sequences. Yeah, and we only care about these lines that start with Atom, so we can filter those, and bam, we've got our PDB file. And currently it's all just one string per line, but we can basically slice that, and it's like, okay, if you slice from this character position, here are your elements. Here's your chain ID. Down here we go, here's our atom ID, and we can turn that into numbers. We can do the same thing for our positions, our X, our Y, and our Z. And then using some fancy closures, we can put together multiple parsers, and we can iterate over our parsers to then, so this is sort of the iteration, the parsing loop, and then that results in some geometry with currently a limited number of attributes because I haven't parsed everything else. But we got our position, we got our atom ID and our atomic number. Look, it's not terrible. A lot of that time is coming from having to convert string attributes into integers before I can store them. So when string attributes become more of a thing, that'll be much nicer. That'll be much faster. But yeah, now we have a parser that's entirely node-based. So 22 milliseconds for, yeah, like 16,000 atoms. Not bad. Hey, how we doing? Yeah, I've just been doing some live streams. I'm spending so much time just messing around trying to improve stuff inside of geometry nodes. I figured I may as well stream it a little bit. Sometimes it's me just noodling around, and I figure I'll keep doing some more. Yeah, I think it's good. I think it'd be nice to have other people doing similar things, and people can just jump on and chat and talk nodes and that sort of thing. We've been trying to really, Quackarooni's been helping me trying to figure out how to do weird stuff with bundles and closures and strings, and having string fields but not string attributes and all that sort of stuff. Clockwork, are we secretly anti-Python? Will it just be better to have this live entirely in geometry nodes? Not real. I mean, in theory, if I can get this working well, then this should in theory be faster than the Python version, but also like there's so many edge cases that I'd rather just like, I don't think anytime soon I'm not gonna looking to replace any of the Python functionality with nodes. This is more being, I was having my coffee this morning and I was like, I think now we have filter list and split list, like split string I can actually make a parser. And so I wanted to just like mess around and see if I could get it working and practice with the closures and bundles and stuff more. Yeah, we got some of the gang here. Yeah, we are getting access to deep molecular nodes law. So this is sort of what I do for fun, is I drink my coffee and I think about how I can exploit new nodes in different ways and then spend forever working on them. But yeah, it's working quite well. So let's continue, because I've shown some people before as well, and we can use strings, list of strings, import values directly on the node using the string option. What? Index switch lets you input values directly on the node using the string option. Where am I doing that? Oh, actually, let's add quickly another bottom left of this node panel currently off screen. Oh, yes, yeah. Yeah, or we could also do hydrogen, helium, lithium, beryllium, boron, etc. And then we can do split by that. And that gives us our list as well. But check out so what I was doing initially to play around with strings to see if I could get things working is a string parser. So we can say residues 1 to 300, and also residues 500 to 700. And you can see we're changing our selection. And also 801 and 802. And you see that changes the selection. Which is basically, again, using some closures, but now we can do so many fun things with closures and strings. We basically get our string, split it by comma, iterate over that, and we either check to see if it's exactly equal to that value, or if I've given so exactly equal to 801 or exactly equal to 802. If there is a dash, then we split it again based on dash and set our min and max and check if we're between that. And then we just iteratively or recursively apply that and get our Boolean selection. So now I can say 500 to 1200. So we can have string selections also inside of geometry nodes. So this is definitely coming in molecular nodes for 5.2. I am unsure if I'll be able to do like res ID 1 to 200, 500 and res name lysine or something like that. In theory, I should be able to do that. Currently, it's very much just like this is only operates on the residue number. But it works really well. But yeah, that was the first thing I did before I started doing this parser. And we're getting a lot of closures. Okay, so we do. Okay, equal. Length. Field to list count. Index. And that gives us that, and we say filter. If we, I think we need to have another closure to list. And this is the length of the and that's hobbits. Okay, so this we need to get list item. Index equal that filter get list item that gives us our integer value Hey, it does. It gives us our integer value for our chain ID. Really gross, but it technically works. This is a very poorly optimized way of going about it. And that definitely makes me think, at least for a custom parser, we should instead go with the bundle of string elements. Because that just removes so much faffing about. Requires changes for some of the things, but I mean, they're not going to be, I'm not going to actually use them, but oh my god, we're almost at 2 hours. I think I'm probably going to call it there for now, because that's enough noodling around. And I got to take the dog out before she pees on the carpet. Thanks everyone for hanging out. This has been very successful. It's been a good little experiment. I'm definitely going to continue with this, and it's given me some ideas for molecular nodes in general that I think we can definitely use. But I'm gonna jump off. Thanks everyone for hanging out. Hope you have enjoyed the noodling. Whoopa. Bye. Oh, very end. Hey Brady, sorry to catch you at the very end. Got to catch up on the previous streams. Yeah. I don't have a schedule or anything, but I'm just sort of jumping on every now and then. So feel free to look back at the previous streams. See you later, Quackaroony. Thanks for hanging out. Bye everyone.